In this video, I will be discussing rational functions, equations, and inequalities. The applications of rational functions are voluminous in more advanced mathematics, such as ring theory and numerical analysis. Rational functions are used to model several phenomena in the life sciences and even in the physical sciences, particularly in engineering, such as forces, electronics, optics, aerodynamics, thermodynamics, and acoustics in physics, spectroscopy, atomic and molecular wave functions, and enzyme kinetics in chemistry, probability distributions in statistics, and even in the field of epidemiology and medicine. Rational functions are likewise used in multiple areas of study to predict outcomes in banking and finance and in economics in general. So first, let us discuss what is really a rational function. So I have written here a definition of a rational function. A rational function, f of x, is a function of the form f of x is equal to p of x divided by q of x, where p of x and q of x are polynomials with no common factor and the q of x must not be equal to 0. The domain of f of x is the set of real numbers such that q of x is not 0. So to illustrate this definition, allow me to give some illustrations through a very short quiz here to check the example and the non-example of a rational function. So number 1, f of x is equal to 1 over x squared. Is this a rational function? If your answer is yes, then you are right because this is a rational function. You see here a ratio of two polynomials. Number 2, f of x is equal to 3x squared minus 2x plus 1 all over x plus 1. Is this a rational function? If your answer is yes, then you are right. This is an example of a rational function because it is a ratio of two polynomials. You see there in the numerator a second degree polynomial, and in the denominator we see a first degree polynomial x plus 1. So it's a ratio of two polynomials. So this is an example of a rational function. Number 3, f of x is equal to x plus 1 over x minus 2. Is this a rational function? If your answer is yes, then you are right because it's a ratio of two polynomials. You see there in the numerator a first degree polynomial and also in the denominator a first degree polynomial. So this is an example of a rational function because it satisfies the definition of a rational function. Number 4, f of x is equal to 2x squared minus 3x minus 2 all over 3. Is this a rational function? If your answer is yes, then you are right because it is a ratio of two polynomials. Because in the numerator you see there a quadratic function and also in the denominator you see there a constant function. So this is an example of a rational function. Number 5, f of x is equal to the square root of x plus 1 all over x cubed plus 2. Is this a rational function? If your answer is yes, then you are not right because you see there that in the numerator we have the square root of x plus 1, and if you convert this one to an exponential form, that is x plus 1 to the power of 1/2. And since the exponent is a fraction 1/2, it fails to be a polynomial because you can recall from the definition of a polynomial that the exponent should be an integer. And since the exponent of x plus 1 is not an integer, but it is a fraction of 1/2, then it fails to be a polynomial. So therefore, this function is not a rational function. Number 6, f of x is equal to 1 over x minus 3 all over x plus 2. Is this a rational function? Before you can answer that, maybe you can just simplify this one so that you can see it clearly whether it is a rational function, because I can multiply the numerator, which is x minus 3, by the reciprocal of the denominator, and the reciprocal of this is 1 over x plus 2, because x plus 2 is understood to have a denominator of 1, and if you get the reciprocal of that, that is 1 over x plus 2. And if you multiply this one, you will have 1 over x minus 3 times x plus 2. There. So you see that it is still a rational function. So if your answer is yes, then you are right. This is an example of a rational function. Number 7, f of x is equal to 1 over x squared minus 4 plus 2. Is this a rational function? If your answer is yes, then you are right, because even though that this rational expression is added to a whole number, but if you combine this rational expression by this whole number, you will still get a ratio of two polynomials. There. So this is an example of a rational function. Number 8, f of x is equal to x squared minus 2 square root of x plus 1 all over x minus 3. Is this a rational function? If your answer is yes, then you are not right, because this is not a rational function because of this square root of x. And you can check that when you express this one into an exponential form, you see that this is x to the power 1/2. And since the exponent of x is not an integer but a fraction 1/2, then it fails to be a polynomial. So therefore, this is not a ratio of two polynomials. Hence, this is not a rational function. Number 9, f of x is equal to the square root of x over x squared minus 1. Is this a rational function? If your answer is yes, then you are not right, because this is not a rational function. And you can check that if you express this one into an exponential form, this is x over x squared minus 1, quantity raised to the power of 1/2. And if you apply the laws of exponents, the exponent of x is 1/2. And since the exponent is not an integer but a fraction 1/2, then it fails to be a polynomial. So therefore, this is not a ratio of two polynomials. Hence, this is not an example of a rational function. Number 10, f of x is equal to 1 over x squared minus x to the power of negative 3. Is this a rational function? If your answer is yes, then you are right, because even though the exponent is negative, but if you convert this one to positive, that is 1 over x cubed. And if you look for the least common denominator between x squared and x cubed, you can convert this difference into a ratio of two polynomials. So this is an example of a rational function. At this point, allow me to give you the difference between the three: the rational functions, rational equations, and rational inequalities. So what's the difference between these three rationals? So first, I have here the definition of a rational function. A rational function is a function of the form f of x, which is equal to p of x over q of x, where p of x and the q of x are polynomials, and the q of x must not be equal to 0. So in simple words, rational function, it's a function that involves a ratio of two polynomials. The numerator is a polynomial and the denominator is also a polynomial. But there is a little condition here that the denominator must not be equal to 0 because division of 0 is not allowed here. So what is a rational equation? A rational equation is not a function but it is an equation involving rational expression. And here, rational inequality, it is not an equation but it is an inequality involving rational expression. So, rational inequality is not a function, is not an equation, but it is an inequality. So, the similarity among the three is that all of them, they involve rational expressions. The only thing is that in the rational function, it's a function. And in the rational equation, it's an equation. And in the rational inequality, it is not an equation, not a function, but it is an inequality. So that's the difference between the three. Now, an example of a rational function is when you have f of x, which is equal to x squared minus 3x minus 2 all over x plus 3. So this is an example of a rational function. Why? Because you see here that the numerator is a polynomial and also the denominator is a polynomial. Then it is a ratio of two polynomials, hence this is a rational expression. And since we have here f of x which is equal to this rational expression, then this is a rational function. An example of a rational equation is when you have 3 over x plus 2 over 5x which is equal to 1 over 7. This is an example of a rational equation. Why? Because you see here 3 over x is a rational expression. 2 over 5x is a rational expression. And this involves equality. So this is an equation. Hence, this is a rational equation. It's an equation that involves rational expressions. Now, also, an example of a rational inequality is when you have 7 over x minus 3 is less than or equal to 2 over x. Now you see in this example that this is an inequality that involves rational expressions. At the left of this inequality, you see it's a rational expression. And also at the right, you see it's a rational expression. And therefore, this is an inequality that involves rational expressions. Hence, this is a rational inequality. So, there will be two things that you need to check here. First is to check whether it involves rational expressions. Now, when it involves a rational expression, try to check whether it is an equality or inequality or a function here. Because in this example, this is a function of x. So the similarity among the three is that they involve rational expressions. But the difference can be found on the symbols used here. We have inequality, an equality, and a function form here. Now, at this point, I will be representing real-life situations, real-life scenario, phenomenon that can be modeled by these three. So, here are some of the situations that can be modeled by rational functions or rational equations or rational inequalities. So, number 1, if Alex and Rod can paint the house together in 5 days and Rod can paint the house alone in 7 days, then how long will it take Alex to paint the same house alone? So first, this is a work problem, and I know that you have learned this one from your junior high school math. So let us represent what is being asked in the problem. So the problem is asking about the number of days for Alex to paint the same house alone. So let us represent it here. Let X be the number of days for Alex to paint the same house alone. So we can represent this problem by an equation of the one whole work. So we say here that 5 over 7 is the part of work done by Rod if they work together with Alex in painting the same house. But if you add the part of work done by Alex, which is 5 over X, then this represents for the one whole work that they will finish for 5 days. So you can see here that this is a problem modeled by a rational equation. So solving this rational equation, we can find the least common denominator, which is the least common multiple between 7 and x, and that is 7x. So 7x divided by 7, it's x times 5, so that is 5x. 7x divided by x, that's 7, but 7 times 5, that is 35. And this is equal to 1. But multiplying both sides of the equation by 7x here, so 7x to the right, multiplying also 7x to the left. So the 7x here at the left will be cancelled, but you will have 5x plus 35, and this is equal to 7x at the right side of the equation. So if you group all the terms having x at the left, you will have 5x minus 7x, which is equal to the negative 35. Because if I subtract both sides of the equation by 7x, the 7x at the right will be cancelled, but I have a 7x at the left side of this equation. And if I subtract both sides of the equation by 35, the positive 35 here will be cancelled at the left, but I will have minus 35 at the right. So subtracting these two, I will have minus 2x. And this is equal to negative 35. So dividing both sides of the equation by negative 2, I will have negative 2x divided by negative 2 here at the left, and also at the right I will divide negative 2. So x here is equal to positive 35 over 2, because a negative divided by negative is positive. Or I can convert this one into a mixed number, which is equal to 17 and 1/2 days. So this is the number of days where Alex can paint the house, the same house, alone. Number 2. A steamboat goes 24 miles upstream and then returns to its original position. The round trip takes 6 hours. The water flows at 3 miles per hour. What is the speed of the boat in still water? So this problem is a problem about distance. And since this is a problem about distance, it involves the distance, the rate, and the time. So let us represent all these things here. So let D be the distance traveled by the steamboat. And let R be the speed of the boat in still water. And also, it involves time. So this is the time spent in traveling by the steamboat. Since we know that the formula for distance is equal to rate times time. And we know also that the distance traveled is 24 miles. Then we say that 24 is equal to rate times time, because the distance traveled is 24 miles by the steamboat. So if you divide both sides by the rate of the speed of the boat in still water, that is 24 divided by r is equal to t. Thus, what can we say? Thus, we say that this time, the time is a function of r, because this is 24 over r. So the time spent in traveling is a function of the speed of the boat. In other words, if the speed is so fast, then the time spent is too short. While when the speed is slow, it has a slower speed, then the time spent is longer, a little bit longer. And you see that this is a problem modeled by a rational function. So to illustrate further, allow me to give a little illustration here. So suppose this is the steamboat here. So the steamboat is moving upstream, which means that this is against the current of the water. So this is the water, and this is the steamboat. When you go upstream, you are against the current of the water. The water is flowing in this direction, the boat is moving against that direction. So of course, the speed of the boat will be changed. So the current of the water will make the speed of the boat a little bit slower. So if you use the information there, the boat is going upstream at a distance of 24 miles and then return at the same position a total of 6 hours. So we say that the time spent in traveling upstream plus the time spent traveling downstream is equal to 6 hours here. But common sense would tell you that the time upstream is not the same time spent downstream, because when you go upstream, your speed will be a little bit slower because you are against the current of the water. So you will incur a little bit longer in time than the downstream. Why? Because in the downstream, you are with the current of the water. So your speed will be a little bit faster. So common sense would tell you that the time upstream is longer than the time spent downstream. Why? Again, because you are against the current of the water. And why is this shorter in time? Because you are with the current of the water. So your speed plus the current of the water, that it flows within your direction. So how will you write that? When you go upstream from this point up to maybe this point, so that distance is 24 miles. So here, if that distance is 24 miles, then of course that is 24 here according to our function, 24 divided by your rate. But your rate in still water will be mitigated because of the current of the water, which is against your direction, and the water is flowing according to the problem 3 miles per hour. So your speed will be mitigated by the current of the water. So mathematically, you will subtract 3 miles per hour. But when you go downstream, again, the distance that you will travel is still 24 miles, because when you are up here and going back, same distance of 24 miles, but your speed is not anymore r minus 3, but this is r plus 3. Why? Because this is your speed in still water plus the current of the water. So your speed will be pushed more by the current of the water. So this is a little bit faster than this speed. So your actual speed plus the current of the water, so your final speed will be a little bit faster as compared to your speed when you go upstream. So this is equal to 6 hours. Because you know, this is the hours spent when you go upstream, and this is also the hours spent when you go downstream, and a total of 6 hours. So solving this one is to find the LCD between the two. So the LCD, or the least common multiple between these two denominators, which is r minus 3 and r plus 3, is this one. So this 1 divided by r minus 3, the quotient is r plus 3, and that will be the one to be multiplied by 24. So 24 times r plus 3. Also this 1 divided by r plus 3, the quotient is r minus 3. And this r minus 3 will be the one to be multiplied to the 24 here. And this is all in all equal to 6. So simplifying this, I know that there are two terms in the numerator and there is a common of 24. So I can factor out the 24. So 24 times the quantity of r plus 3 plus r minus 3 there. And you can check that when I multiply 24 to these two terms here, there and there, you will get this one. So copying the denominator, I will have r minus 3 times r plus 3, which is equal to 6. And multiplying both sides of the equation by 1 over 24, so here I will multiply 1 over 24 at the right and 1 over 24 at the left. This 24 at the left will be cancelled. So what will remain is just r plus 3 plus r minus 3 here. And this is still divided by r minus 3 times r plus 3. And this is equal to 6 over 24, because 6 times 1 is 6 over 24. Now, removing the parentheses here, I will have 2r plus 3 minus 3, because r plus r is 2r. So this is just 2r in the numerator. And you can also simplify this one to its simplest form, which is 1/4. Because if you divide 6 by 6, that's 1, and 24 by 6 is 4. So this is 2r over, if you multiply these two binomials, that's the sum and difference of two terms. So this is r squared minus 9, which is equal to 1/4. And then when I multiply both sides of the equation by 4 here, I will have 8r over r squared minus 9, because 4 times 2r it's 8r. But at the right you will have 1, because 1 times 4 it's 4 divided by 4, that is equivalent to 1. And then if you multiply both sides of the equation by r squared minus 9, this is equal to 8r, which is equal to r squared minus 9. And subtracting both sides of the equation by 8r, the 8r at the left will be cancelled. So what will remain is just 0. So this is r squared minus 8r minus 9. So I will have minus 8r at the right when I subtract both sides of the equation by 8r. And you see that this is a quadratic equation where I can factor this one as r times r as the factors of r squared. And the factors of negative 9 to get negative 8, it's negative 9 plus 1. And you can check because r times r, that's r squared. And negative 9 times 1, that's negative 9. But to get negative 8, I need to have negative 9r plus 1r, and that is negative 8r. So our factoring is correct. So equating each factor to 0, r minus 9 equals 0, and r plus 1 equals 0. But this one, the r is 9. However, the other one, the r value is negative 1. But the answer is this because the rate or the speed of the boat in still water must be positive. So this is not a solution of the problem because this is a negative. So this is the speed of the boat in still water. So let's proceed to this third problem. The maximum safe load for a horizontal beam supported at each end varies directly as the width and the square of the depth, and inversely as the distance between the supports. If 1,800 pounds is the maximum safe load for a beam 3 inches wide and 6 inches deep and held by supports 15 feet apart, then what are the safe loads compatible for a beam 2 inches wide and 4 inches deep with supports 10 feet apart? So, how are you going to solve this problem? So first, let us maybe illustrate the problem using a drawing. So, I will draw here a beam wherein the width is 3 inches. So here is the 3 inches. And then it has a depth of 6 inches. There. But this is supported by, so this beam is supported by these two supports which of distance 15 feet apart. So here 15 feet apart. So first, let us represent the variables in this problem. So here, let L be the maximum safe load. And the width, so let us represent that one as W. And also, the depth will represent that one as D. And also, the length of the beam. So, because we use already D, so the distance between the two supports will represent using another variable, say S. So this is the length or the distance between the two supports. So we say that this is the length of the beam. And according to the problem, that the maximum safe load varies directly as the width of the beam and the square of the depth, and inversely to the distance between the two supports. And of course, there is what we call the constant of proportionality, K. And I know that you learned this one from your junior high, that in a variation, there is what we call the constant of proportionality. So let K be the constant of proportionality. And according to the problem, that when the load is 1,800 pounds, it is the maximum load for a beam of 3 inches wide and 6 inches deep, with the distance between the two supports, which is 15. So when you substitute these values here in the equation, we have 1,800, which is equal to K, which we don't know, times the width of the beam, which is 3 inches, times the depth of the beam, which is 6, but this is squared, divided by the distance between the two supports, which is 15 feet apart. So when you multiply both sides of the equation by 15, I will have here 15 times 1,800. And here, I will have k times 3 times 36 because the square of 6 is 36. But I don't have any more 15 because when I multiply both sides of the equation by 15, this 15 will be cancelled out. So multiplying 15 by 1,800, we have 27,000. And this is equal to 36 times 3, which is equal to 108. And then multiplied by k. So therefore, k is equal to 27,000 divided by 108. And if you divide this one, you will have a quotient of 250. So 250 is our constant of proportionality. Therefore, I can substitute this one here in our formula. So thus, we have the maximum safe load is equal to 250, because that is the value of k, times the width of the beam times the square of the depth of the beam, and divided by the distance between the two supports. But since the problem is asking what are the safe loads compatible, so it is not only one load. So the maximum and all the loads that are lower than that, so I will have this inequality. So L is less than or equal to this value. In other words, the loads that are compatible with this new beam can be represented by this. It can be equal or less than, because if the load is less, then it is still okay with that beam. So you see that this is a problem modeled by a rational inequality. So if the beam is having a width of 2 inches and the depth of 4 inches, and also the distance between the two supports, which is 10 feet apart, then I can compute all the loads that are compatible with this beam. The load is less than or equal to 250, the constant of proportionality, multiplied by 2 times the depth of the beam, which is 4, but we need to square it, divided by 10, which is the distance between the two supports. So the load, which is equal or less than 500, because 250 times 2, that's 500, times 16, because 4 squared is 16, divided by 10. So the load, which is less than or equal to 500 divided by 10, that is 50 times 16. Or in other words, the load is less than or equal to 800 pounds. So what are the loads compatible with the beam of width 2 inches, of depth 4 inches, and the distance between the two supports of 10 feet? It's 800 pounds or less. Are the loads compatible with that beam? So in other words, we say that at most 800 pounds is the maximum safe load. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.